All right, there's basically one final configuration where we can easily do a calculation to find the capacitance, and that is in the case of a sphere. So imagine that we have a spherical conducting shell that is surrounding another spherical conductor like this. So I'm going to have some positive charge on the inner shell and then some negative charge on the outer shell, equal and opposite amounts. So this will be plus Q on the inner shell and minus Q on the outer shell. Okay, so what I would like to do is remind you first that the electric field here is 1 over 4 pi epsilon naught times whatever the charge is, so Q over R squared. And that'll be the case in between the two shells. Outside the shells, the electric field will be 0 because there will be no charge enclosed by a spherical Gaussian surface. Okay, so if I want to find the magnitude of delta V here, then what I'm going to do is I'm going to integrate that electric field. So I'm going to take the magnitude of negative integral of Q over 4 pi epsilon naught R squared dr. Why dr? Well, I'm going to integrate from one shell to the other, and that's along the R radius. Okay, so I'm going to integrate from the inner to the outer diameter, or radius, I should say. And that's a pretty simple integral to do. I should close my absolute value here. And essentially what we get is 1 over 4 pi epsilon naught times Q over R outer minus Q over R inner. And R outer is bigger, so this actually gives me a negative value, and since I wanted the absolute value, I'm going to switch the order. So R inner minus R outer. Okay, and that gives me a positive number. Okay, so to find the capacitance then, C is equal to Q over delta V, which is going to be Q over 1 over 4 pi epsilon naught times Q over Ri minus Q over Ro. And if you do a little bit of algebra, then you'll get 4 pi epsilon naught over 1 over Ri minus 1 over Ro. And that's basically the final form. If you check against the formula that's provided in the textbook, it's a slightly different algebraic arrangement of it. I think it's anyone's choice which one is the simpler way to write it. Okay, so in general, this is actually an example that kind of annoys me because you can't actually build a spherical capacitor. You would need to have something that was supporting the inner part, and then if you were actually charging it to some amount, you're putting charge on the positive inner part, how do you get the charge there? There'd have to be a hole, and then you've ruined the spherical symmetry. However, there is something really interesting to notice here. So let's say that the outer radius we take to 0. All right, so even if R0 goes to, let's take that to infinity. So we want to make the outer sphere super, super big. Okay, so if we do that, then it turns out the capacitance does not go to 0. So if we take the outer radius to infinity, then the capacitance becomes 4 pi epsilon naught over 1 over R. So that's just going to be Ri. All right, so the capacitance is not 0 even in that case, which the conclusion of which is that even an isolated conductor where there is even no outer shell, because we take it as far away as we want, is still going to have a capacitance. So the takeaway is that an isolated conductor has capacitance. Okay, and that's a really surprising result, I think. We defined capacitance in terms of there being two conductors, and it's this interaction between the two conductors. But now we're saying that even if you only have one conductor and nothing else that we are interested in, that conductor alone still has some capacitance, just relative to the rest of the universe around it. And the reason that's important, again, is if you're thinking about going into electrical engineering, for instance, even things like just ordinary wires that are connecting different parts together, or resistors or any other component, always is going to have some non-zero capacitance, and that can have unintended consequences. So, even if you're trying to build a really, really simple circuit, it turns out there are still these details that will make even a simple circuit fairly complicated. And so it turns out all materials, all objects have some resistance, all objects have some capacitance. And then there's a third quantity, which we're not going to get to in this class, but when you go on to take 123, you'll learn about inductance, and it turns out all materials will also have some inductance. And so those are the three basic electrical properties that people are interested in, and even a really simple object like a wire is going to have all three, even if you don't actually want it to.